that we all know is enormous generosity, energy in communicating his passion for study and research. I think that several generations of algebraic geometers are indebted to him for advice and example. So let me leave him the word. He will talk today about nodal surfaces, coding theory, and cubic discriminants.
Okay. Thanks a lot, Ciro, for the nice introduction. This, in fact, is a paper which is, I hope, will be shortly on archive, except that its size is growing. It's over 140 pages, and I hope to be finished soon without mistakes. And it's dedicated to Ciro, so I'm very happy about it. And, thanks for the presentation. Reminds me of an old joke by Louis Nirenberg, where the old professor during this falls asleep and then suddenly wakes up and says, "Oh, but you didn't say anything about his modesty." Anyhow, so let's start with the joke. And so this is a project. Actually, nodal surfaces is something I started to work when I was in Harvard, 77, 78. And I've been through the years collecting a lot of results. And recently, in Bayreuth, I decided to revive this with a group of people. And it's been an incredible synergy of different directions: computer science, coding theory, and of course, algebraic geometry, and so on. So anyhow, let me begin. So this is the title, and there will be 5 chapters: the introduction, then I will talk about binary codes, then quintics surfaces, sextic surfaces, and then in the end, cubic discriminants. So I hope that at least the first part of the talk will be understandable for everyone. In case there are problems, interrupt me, ask a question, and if I hear well your question, I will try to answer it. At any rate, I organized the talk that even if you get lost at some point, there will be something more concrete to wake up later on. So let me begin. Nodal hypersurfaces. So throughout the lecture, I consider homogeneous polynomials f of n plus 1 variables, x0, xn, of degree d. And to this, one associates an hypersurface of degree d. In the projective space, here this n and this n should be the same. In projective space, you take the 0 set of this polynomial. So the object is quite well-known, familiar, but I will consider complex numbers. Now, we say that the hypersurface has isolated singularities if the locus of points where all partial derivatives vanish is a finite set. So we are in a special case of this situation. Now, what is a node? I want to explain what is nodal hypersurface. A hypersurface is nodal if its singular points are just nodes, as I write here in blue, and the singular point x star, the vector x star in the singular set, is a node if the quadratic part of the Taylor development of f at x star is of maximal rank. This is well known, except you have to take projective space as dimension n. So the maximal rank is n, even if you have n plus 1 variables, you have the relation for homogeneous functions given by Euler, that the sum of xi times the partial derivative is the degree of the polynomials times f. And so the maximum rank is n, and this means that the m+1 gradients of the partial derivatives have rank equal n. So this is the easiest singularity which you can have. And they are also known in analysis, in bifurcation theory. So we concentrate on this. Now we go to the name. I propose a new name, Nodal Severity Variety. F stands for family, N stands for the dimension, D for the degree, and N for the number of nodes. We take inside the projective space parametrizing whole hypersurfaces. Hypersurfaces are given by polynomials. Polynomials are a vector space, so you have a projective space. We take hypersurfaces in Pm+1, so hypersurface X has dimension n, and we take there the locally closed set consisting of the nodal hypersurfaces X of degree d and dimension n with exactly n nodes as singularities. Why the name Severi? Severi started the case of n equal 1 of plane curves. In this case, one has to add the hypothesis that X is irreducible, which means that the polynomial is prime. And it turns out that the variety, this Severi variety for dimension 1 is non-empty if and only if the number of nodes is bounded by d-1, d-2 divided by 2, and is smooth and connected. So everything is wonderful for curves. This is what Enrico said, yeah? Curves were invented by God, and this neuther and the surfaces by the devil. However, this is a famous statement, but in the Vorlesungen of Severi, in the appendix F, there was an incomplete proof, and it was rescued only some 60 years later by several people with different methods, analysis, geometry, and so on. Now, the name, I'm a little bit stealing the name. Many colleagues in Rome, Ciro, Flaminio, Edoardo Cernesi, and so on, extended the investigation case of nodal curves lying on other algebraic surfaces, which is also a quite beautiful subject. But I will go to higher dimension. So let me give, I'm very bad with the computer, so I just made the stupid picture, but this picture is supposed to give something, a flavor. Let me take an elementary example. We take this in the space of plane conics, the diagonal conics. So these are the zero sets of a sum of 3 squares. A0 x0 squared plus a1 x1 squared plus a2 x2 squared equals 0. Now, if you multiply the a's by a constant, the curve doesn't change. So the parameter space is another projective plane, which I denote by PA, and the vector 0, a1, a2. And inside, we have the variety of one nodal diagonal conics. Now, a conic is singular if and only if the determinant of this diagonal matrix, a0, a1, a2, vanishes. When it vanishes, we have just these 3 lines, a0 equals 0, a1 equal 1, each coordinate equal to 0. But if both vanishes, then of course if a1 and a2 vanishes, I get a line with multiplicity 2. So the one nodal diagonal conics are just this triangle minus these 3 vertices. So you should think that we have a very complicated parameter space, but we would like to have a similar picture. The connected components of the nodal variety, and also we want to understand, we get a stratification of this projective plane. Outside, there are the smooth conics. On the lines, but not on the vertices, we have the pairs of lines. Maybe I can, yeah? And on these 2 vertices, we have the double lines. And for instance, on this line, we have the pencil spanned by this double line and this double line. Okay? So this is just a picture. I will not make more pictures, but you should think that I want to understand, for instance, I want to understand when this stratum here is in the closure of this line and this line, but not of this other line. So we want to understand the stratification in the space of polynomials, and also which stratum is in the boundary of the other one. Okay, so this picture should motivate somehow the quest that we are looking for, understanding how certain strata go together. Now, what are the basic questions for Nodal Severi varieties of hypersurfaces? And these questions are almost completely open for n at least 2, because there is no miracle in, I mean, everything. I mean, I like very much when I started to study one complex variable, because everything works perfectly. But life is tough as soon as you go to a higher dimension. First question, when is this variety non-empty? We have seen already for curves there is some inequality for Ni. Since this variety has a finite number, if I fix n and d, well, we have a variety, it has a finite number of components, so there is a maximum of the Ni such that this variety is non-empty. And this is called mu n of d. And the difficult question is to determine this number explicitly. Another question is, well, you know, assume you find what is the maximum. Are there gaps? So for which values of n and d do we have the no gaps phenomenon that this variety is non-empty for all the numbers Ni not greater than the maximum? And more refined questions, when is this variety connected or irreducible? How can we determine its components? When is it smooth? So there is a lot of questions, and I want to revive interest for this question. So let's start. I will devote myself to the next case, which is already incredibly complicated. Difficult and wide open is the case of surfaces. So a vague idea of the state of the art. This number, the maximum number of nodes that the surface of degree d can have, this is known only for degree up to 6. And okay, a plane has no singularities. An irreducible quadric has at most one singular point. For a cubic, you can have at most 4 singular points, 16 for the quartics, 31 for the quintics, and 65 for the sextics. There is a lot of history starting from the 19th century. So for d equals 3, there is only one, and is given by the third elementary symmetric function, and is called the Cayley cubic, even if apparently it was first found by Schläfli, and it has been studied also by Cremona and Cayley. Again, in the 19th century, for d equals 4, the maximum is given by the Kummer surfaces, which have 16 nodes, and the first examples were found by Fresnel in 1822. For the next degree, we go to the last century. The Togliatti quintics, in 1940, Togliatti showed that there are quintics with 31 nodes, and Beauville in 1979 showed that the maximum is smaller than 31, so the maximum is 31. And he introduced coding theory. For d equals 6, Barth gave an example with 65 nodes, and Jeffy and Ruberman showed that the maximum is just 65. The proof was quite complicated, and the proof was then simplified by Johnny Wall and then Pignatelli and Tonoli, and they are using something quite easy for coding theories called the Mcwillians identities. But there were some very hard steps, which I will describe later. And now for degree up to 6, there are no gaps. And this goes back to work which I did with Ceresa in 79 for n equals 6, constructed all possible number of nodes between 1 and 64. The case of quartics goes back to Ron in 1886 for n equals 4. And however, there is a new result for the case of quintics. So degree up to 6 surfaces, we have no gaps phenomenon for nodal surfaces. So for each ni between 1 and mu of d, there exists a nodal surface of degree d with precisely ni nodes. Now, the case of cubic surfaces is classical, and the Nodal Severi varieties are smooth and irreducible. So we go to degree 4. Now, in spite of many books written on the topic, the question was completely open up to now. We are able to classify the irreducible components of the variety of quartic surfaces with ni nodes for each ni at most 16. So I will first give the statement to see what is the result. Then I will explain the words in the statement. And after that, I will comment about the proof. So take a nodal quartic surface in P3 with ni nodes. And of course, ni is at most 16. And we set Y star the smooth part, the complement of the singular set. The first result is that if the nodes are at most 15, the fundamental group of the Poincaré group, fundamental group of the smooth part is finite and is just Z2 to the power K. This fundamental group is isomorphic to the binary code of the surface, which is in turn determined by the dimension K, exactly this. For 16 nodes, this is classical. So 1 is a new result, 3 is known. But we want to mention that for 16 nodes, this group is infinite. It's just the semi-direct product of Z to the 4 times Z mod 2. So we have Z mod 2x on this free abelian group by multiplication by -1. And here, the codes are the so-called, I call it Kummer codes. I will later explain how they are known in coding theory. And now, if you take the Nodal Severi variety of quartics, you fix the number of nodes, and you fix the binary code K prime, this is smooth and connected. So the code determines this component. And we can completely classify the possible codes K prime. These are all the shortenings of the extended Kummer code K prime. So I will explain what is the shortening. This is a very important, simple idea, which anyhow, something disappeared. Okay, I can also do. Then, okay, let me repeat. We have a complete geometrical description. The subset of the nodal severity variety corresponding to surfaces with fixed binary code is smooth and connected. The possible codes appearing, they are exactly all the shortenings of the extended Kummer code. And to give a flavor of the power, the Nodal Severi variety has exactly one irreducible component for 0, 1, up to 5 nodes, and 16, 15, and 14. In the middle, we get 2 irreducible components when the number of nodes is 6, 7, 13, 3 irreducible components for ni equal 8, 9, 4 components for ni equal 1, 11, 12, and in the middle for n equal 10 fiber reducible components. So we have, like in the picture I showed, we have a stratification of the this open set of the quartics made of 34 strata, and we can also describe this stratification because every stratum is in the boundary of another if and only if the corresponding extended code K prime is a shortening of the admits the other as a shortening. So this concept of shortening, I will later say, I will ruin the suspense, but shortening is the equivalent of the geometrical concept of small deformation. Now, I want to explain the statement of the Nodal theorem, so I will go to basic notions of coding theory, and especially binary code. So I take a field F, and an F linear code is a vector subspace K of dimension small k, so script K and is the subspace of a space of functions, so the F-valued functions on a given set S. And two such codes, K1 and K2, are equivalent if and only if there is a bijection between the two sets carrying one to the other. So really, you should think that codes are just, well, functions with values 0, 1, like in the Morse alphabet. And sorry, if we have the Morse alphabet comes out if I take a binary code. So I take the field with two elements, 0 and 1, Z modulo 2. Now we come to the important but easy concept. A code, given a code, I take a subset of the set where these functions are defined, and the shortening with respect to n is just the set, the subspace of functions with support in n. So it's k intersected f to the n. Whereas given functions on S, I can restrict them to function on S, I can restrict them to n. So the projection of k determined by n is just the image of k via the restriction map. I take functions on S and I take the induced function on n. So the shortening with respect to n is just the kernel of this projection. Okay, so I hope you remember that the shortening means just you take the subspace where it's zeros, we get only zeros outside of n. And of course, every code, you can always enlarge it with zeros. So this motivates the next definition. The effective length n of k is the cardinality of the union of the supports of all these functions in k. And for a single vector, which is a function, the weight, also called Hamming weight, is just the cardinality of the support of the function. The minimum weight is the minimum of the weights of the non-zero vectors. And this minimal weight is also called the Hamming distance of the code, because when you have you want an error correcting code, you can correct as many mistakes as the half of this weight. So that's why Hamming introduced some codes. And since k is contained in the space of functions on f to the s, dually we have a surjection from f to the s to the dual. But the dual code is like dual in the sense of projective geometry, is the kernel of phi. So this is just, in other words, is the perpendicular subspace in fs to k. And if you take duality exchanges projection with shortening, this is not very important, but I mean, it's just a formal property. Now, let's start with the simplex code, which is the easiest code, which I like to explain also in the lectures of linear algebra. The biduality code is just the natural embedding of K in the set of functions on the complement of 0 in the dual subspace. So we know that K is K gives linear functions on the dual subspace. So each non-zero vector is a linear form on K dual. So it takes half of the time the value 1, and half of the time the value 0, but we are removing 0. So you see that the weight is exactly 2 to the K minus 1. So this is a code where there is only one weight. Now, its dual code is called the Hamming code. And this simple code, biduality code, is also called simplex code. But in many books, like Van Lint, is called the dual Hamming code, which somehow is faithful to history, because Hamming first introduced the complicated code, and then they took the dual one. But I mean, it's much simpler to do the other way around. And now to a code, one associates a polynomial, the weight enumerator function. You take a polynomial with coefficients, the number of vectors of K with weight equal to I. And the fundamental discovery of Mcwillians, the Mcwillians identity, determines the relation between the weight enumerator of the code and the weight enumerator of the dual code. The weight enumerator of the dual code is 1 over 2 to the K. K is the dimension of the original code. And then you take the weight enumerator, but evaluated in x plus y, x minus y. So this is a very compact presentation of this identity, but of course you can equate all the coefficients. So let me explain how is important the Mcwillians identity. Okay, so this is quite easy, but maybe some people don't know it. I want to show how to use the Mcwillians identity. Now, the first two identities are just the sum of the AI for I different from 0 is 2 to the K minus 1. And the sum of I AI is the effective length times 2 to the K minus 1. So we just use this. Now, assume that we have a code where all the weights are just a power of 2. Let K be the dimension of K and its effective length. Now, the second Mcwillians identity, we have only one weight, 2 to the M, is gotten for all vectors except 0. These are 2 to the K minus 1. And this is 2 to the power K minus 1. I always make a mistake in writing, times N. Okay, N is an integer, and it is 2 to the K minus 1, an odd number, times 2 with exponent M minus K plus 1. But N is an integer and not a rational number, so K is at most M plus 1. So this is the very nice application of the Mcwillians identity. And with a little bit more work, you can also prove that if K is equal to M plus 1, we have the simplex code in general, and in general, a subcode of the simplex code. And this was generalized by Bonisoli, who showed that each code with only one weight is gotten from the simplest code just by taking functions of taking a Cartesian product and saying that V of xy is V of y. Okay, so this is a very simple but nice theorem of Bonisoli, which explains that we know everything about codes with one weight. And then there are work, of course, with two. Now, for my purpose, I need a new type of codes, and a bicolored F linear code is just you take a vector subspace K prime, of the vector space of functions on the disjoint union on A and B. And again, these are equivalent if there are bijections of A1 with A2 and B1, B2 carrying the first code K prime 1 to the second. In my situation, B shall consist of a single element H. The letter H stands for hyperplane section, and moreover, often K prime is determined by its projection K double prime inside F of A. So sometimes one describes K prime, sometimes one describes K double prime. Now we have seen that linear functions, they describe the first code, simple code. Now let's go to quadratic functions, polynomials of degree at most 2. Now we take in a fine space of dimension m over the field with 2 elements. So A is essentially f2 to the m, except that you're not fixing the origin. Then the first Reed-Muller code is the space of affine functions from A to f2. So f is just a linear function, sum of aixi plus a constant. And the second Reed-Muller code is the space generated by the first Reed-Muller code and a non-degenerate quadratic form. And of course, the dimension of K is m plus 1, and the dimension of K double prime is m plus 2. And the Kummer code, respectively the extended Kummer code, are just the case m equals 4. Okay, so the codes of Kummer surfaces, they are described by some easy bilinear algebra. In fact, there is some bilinear algebra over a field with 2 elements that says that you can really replace Q by some, if M is 2H or 2H plus 1, you just take QH is X1, Y1 plus X2, Y2 until XH, YH. And the main point is that each polynomial function of degree 2 over F2, these are quadratic forms over a field of 2 elements, and so we have different affine normal form, either the previous Q plus XK plus 1 squared, or just this plus 1. So these are the normal forms, and if M is equal to 2K, there are 2 cases, 1 and 2, and I mentioned this, they differ because in the even case, 1, the number of zeros equals 2 to the K minus 1 times 2 to the power K plus 1, and in the case it equals the same power of 2, but now you take 2 to the K minus 1. I'm mentioning this because these numbers are well known to geometers, because are just the number of even or odd theta characteristics of algebraic curves. Now, now we come to something a little bit hard. So how do we associate to a nodal surface a binary code? There are several ways, but the most topological one is I get a nodal surface in P3, then the binary code K in Z2 to the Ni is defined through the dual map to this surjection of the direct sum of Z mod 2. This is a homology around the nodes. This goes to a homology of the first part. And if you blow up Y at the nodes, and H is a smooth hyperplane section, then the extended binary code is the kernel of the map. So you take the vector space generated over Z mod 2, generated by these exceptional curves coming from the nodes and H, and you take the kernel of the map in the second homology of this blow up in Z mod 2. So this you have to believe. It's so why is this important? So there are many ways, but this is important because it shows that these codes are topological invariants. So again, I repeat what I said. This is the definition of K prime. The important thing is that K prime you take now the cohomology of y tilde with coefficients in Z, and there you take the lattice generated by the classes of the curves EI and H, and then K prime determines the saturation. So the saturations are just the elements in lambda such that a multiple is in L. So is lambda intersected QL. Are the elements in lambda which are rational multiples of that. And the answer is quite easy. The saturations are just 1/2 of the sums of the AIs and H, such that this sum, modulo 2, gives an element in K prime. So, you know, this is something, there is a famous book by Conway and Adler and Sloan. There is a relation, an obvious relation between coding theory and lattice theorem. This is not well known. At the basis of all the works of Borchers and others, there is this deep relations between coding codes, binary codes, and lattices. So I am on page, I am sort of 27, 28. So for nodal surfaces with a minimal resolution y tilde, the lattice contains the sublattice generated by EI and H, and the extended code K prime determines the saturation. This lattice is important because it's primitively embedded. So this is a very important piece of work done in the 70s. Actually, it's the most important work of Slava Nikulin. He generalized results of Milnor and others. The Milnor, for topological applications, studied unimodular quadratic forms. Non-unimodular were treated by Nikulin, and he described a theory of primitive embeddings of lattices. And these results offer criteria for existence and unicity of such embeddings. Now, these results are very useful for K3 surfaces, of which resolutions of nodal quartic surfaces are a special case. K3 surfaces are simply connected smooth surfaces with trivial canonical bundle, and Kodaira shows that these are the deformations of smooth quartic surfaces. And K3 stays for Kummer, Keller, and Kodaira, who studied these surfaces. And for them, now if we fix the cohomology of y tilde as a fixed lattice and the extended code by the results of Nikulin, there is a unique primitive embedding of this saturation inside lambda. So here, a most important theorem for K3 surfaces is the Torelli Theorem. And this shows that the nodal quartic surfaces with the fixed code K prime are parametrized by at most 2 smooth connected components exchanged by complex conjugation. Bože moj. But we want to show that these 2 components are the same. And since they are exchanged by complex conjugation, it suffices to show that exists such a quartic which is real. How do we do this? And so this is now something also non-experts can have a look at. So my father was born in Cefalù, and so I decided to find this name for this Kummer quartic surface. I mean, they are intimidating. Kummer surfaces are the quartic surfaces with 16 nodes. They are the quotient of a principally polarized abelian surface by ±1. But now, let me give you the simplest example, important for many reasons, of a quartic with 16 double points. I take the sum of the squares squared minus 3 times the sums of the 4th power. This is a simple equation, and the 16 singular points are just the points where there exist 1, 0, 1, 1, and the others are ±1. So these are cyclical permutations of the 4 points which have coordinates 0, 1, ±1, ±1. And this surface has a lot of symmetries. Z2 to the cube times the permutation group in 4 elements. The upshot is that the equations and the singular points, I mean, you see the coefficients are just 1 or 3, here plus minus 1. So everything is defined over the integers, and y is unobstructed. And from this, it follows that for each ni at most 16, you can find these quartic surfaces with exactly ni nodes for each k prime. So this explains the theorem. The subset of the nodal variety corresponding to surfaces with fixed binary code is smoothed connected. Here I go a little bit faster because this is for experts. This follows from the Torelli Theorem plus the reality condition and Mcwillians results. And however, the theorem is not finished because you have to classify all the possible codes appearing and show that they are shortenings of the extended Kummer code. And once you have done this classification, you find that you have 34 strata, and each stratum is in the boundary of another if and only if the corresponding extended code admits the other as a shortening. But let me point out that this is the key new idea. A deformation yt of a nodal surface by which only a subset nt of n of the nodal set remains singular leads to kt being a shortening of k. And the same methods allow description for the Severi varieties of nodal K3 surfaces. The results are similar, but the codes depend on the residue class modulo 8, and there are some sporadic cases. It is fun to look at the case of d equal 2 because you have double coverings of the plane branched on a sextic curve, and you have to describe the sextic curve with nodes. And the case of degree 6 is the case of complete intersection of type 2-3 in P4, very important because these surfaces are obtained from a nodal cubic hypersurface, taking the Taylor development of the equation at some node. Now, the main question for the classification is to find what are the possible weights. And for this, it's important from codes, we pass, if the function has values 0 and 1, the function is determined by its support. And the support is called an even set of nodes. If you have a vector in K, it means that the sum of the AI is divisible by 2, or half even if this sum plus the hyperplexion is divisible by 2. And the main important thing is that by the, here comes algebraic geometry, the cardinality of an even set of nodes is always divisible by 4 and divisible by 8 if D is even. And with Casnati, we were able to give a structure theorem for this even and half even set of nodes. They come from a symmetric map of a vector bundle in E, so E. And this map has the property that the rank drops by at least 1 on the points of the surface, and the set of nodes is where the rank drops by 2. Now, the nodal set is said to be symmetric if E is a direct sum of line bundles, which means that alpha is a matrix of polynomials. Okay. With this theorem, we show that I showed 78 that for D equals 5, the only possible weights are T 2016, and they correspond either to a matrix 5 by 5 of linear forms or with diagonal degrees 1, 1, 3. And together with Sandro Verra, we showed that if a nodal quintic has an even set of cardinality 20, its number of nodes is at most 28. And the case where n equals 28 via prime theory leads to an irreducible component of this nodal variety. Now, let me explain, even if time is running, this provides a very simple proof of the theorem of Beauville that the nodal quintic has at most 31 nodes. And, well, we want to show that the maximum is 31. So if n is an even set of nodes on a nodal quintic with new at least 21 nodes, by the previous theorem, the cardinality of the set is 16. So we have a code with only weight 16. And I showed before that the code of Y is a subcode of the biduality code. In particularly, its dimension is at most 5. However, Beauville observed that the dimension is at least the number of nodes minus 1/2 of the second Betti number of Y tilde, because it's a kernel of a certain map of vector spaces. And this is just Ni minus 26. And since K is at most 5, 5 is bigger than Ni minus 26, so Ni is at most 31, equality holding if you have the biduality code. And the existence of a quintic with 31 nodes was shown by Eugenio Togliatti in 1940. He didn't verify all the details, and there are discriminants of the projection of a cubic hypersurface in P5 with 15 nodes from a general line contained in it. This is the method of the cubic discriminants, which I explain in the end. Barth found an explicit equation of a quintic with 31 nodes, but only recently Kaplan and Frapport in Bayreuth used the method of Togliatti to find an explicit determinantal equation. Here is this nice equation. You have a 3 by 3 matrix. It's symmetrical, so you don't repeat what is here. These are linear forms. This is a cubic form. This cubic form defines the Cayley cubic, and the notation is that S1 is the sum of the yi's, the first Newton function, and S3 is the third Newton function. Anyhow, so there is an explicit equation. This is nice. And for nodal quintics, we understand, we can prove that the Nodal Severi varieties are irreducible for quintics with 31 nodes and cubic hypersurface in P5 with 15 nodes, Togliatti cubics. And then there is some correspondence between these sets if you take quintics with D nodes and cubic hypersurfaces with Ni minus 16 nodes. And there is a complete description of all possible codes of quintic surfaces, not all the connected components, but there is an open question. There is a unique dimensional code, so with exactly 2 code words of weight 16, and we don't know whether this happens. This occurs. Now, next we go to the Barth sextic. The Barth sextic has a very simple equation. Tau is the inverse of the golden ratio. Then we get the product of these 3 linear forms, this quadratic form and W. These are the invariants for the studied by Felix Klein for the action of the icosahedral group. Now, this equation shows something. There are 6 planes intersecting Y in a cubic counted with multiplicity 2. So if I set tau x minus y equals 0, you see that this first term vanishes. So we get this 0 set, and you see everything is a square. So I get the square of W times the restriction of this. And on this plane lie the 15 nodes defined by the vanishing of this cubic polynomial and this quintic polynomial, which is the left-hand side, these 6-degree polynomials defined by this. So this equation shows that there are many half-even sets of cardinality 15. And we have 5 more, we have 6 of these planes, then we use the orbit by the icosahedron group, which is the alternating group in 5 letters. And Yongwa Cho, who has been in Bayreuth as a postdoc, that the projection of the extended code of the bar sextic is generated by the half-even sets of cardinality 15. And in this way, it was possible to write the code explicitly. And however, the question was, well, when you get, I mean, when I get a list, I mean, I had some colleagues and I asked them some question and I get a computer list, and this for me is not satisfactory. But I mean, Kiermaier here in Bayreuth made a very nice observation that the code of the bar sextic is isomorphic to the code generated by the characteristic functions of maximal independent sets of the Doro Hall graph. There is a graph. There you take all the maximal sets such that no edge joins to vertices. This is found by Yongwa, actually. And then you take these functions. Now, this Doro Hall graph is very famous because it's a regular graph with 65 vertices, which is locally Petersen, and has the property that each vertex has 10, 30 at distance 2, 24 at distance 3. And the code K is generated by the characteristic functions of the 65 spheres of radius 3. So you take a vertex, you take the 24 points at distance 3, and this generates K. Now, locally Petersen means the following. Is this something disappeared? So this Doro Hall graph was constructed by Doro via group theory. You take the group generated of collineations over the projective line of a field with 25 elements. You have all the projectivities and the semi-projectivity which are induced by the Frobenius. Frobenius F25 is obtained by the field with 5 elements adjoining the square root of 2, and Frobenius sends the square root of 2 to minus the square root. Doro constructed the set of vertices as a conjugacy class of Frobenius, where an edge connects two elements if and only if they commute. This is beautiful, but Hall later showed that classified completely the so-called locally Petersen graphs. The graphs which locally are like the Petersen graph, and the Petersen graph is a graph associated to the vertices of the projective dodecahedron, which is the quotient of the dodecahedron by the antipodal map. Now, what is beautiful is that the bar surface allows to reconstruct this graph. You take the bar sextic and you associate a graph whose vertices are the nodes where an edge joins two vertices if and only if the line intersects y, the surface, in 4 distinct points. Then this graph is isometric to the Doro Hall graph. So, and all this was found by computer calculations. It's completely beautiful. We have not only an explicit description, but some conceptual. What is only missing is that the Petersen graph is related to the dodecahedron, which is dual to the icosahedron. So, and the symmetry of the bar surface is given by the icosahedron. So the question is that, is there a direct explanation for this mysterious coincidence? And well, this is beautiful, but I hope in the future will be solved. Now, if you look at sexty surfaces with 65 nodes, I mean, there was work of several people, and finally with Tonoli, we proved that the cardinalities of even sets of nodes on a sextic are exactly the elements of the set 24, 32, 40, 56. And with this, and with a very strong Linux cluster, and I think computer time of 1 year, Sasha Kurz and others, they proved that the codes of a nodal sextic with 65 nodes are isomorphic to the ones of the bar sextic. So you see here, there's been projective geometry, topology, coding theory, but here now it comes hardcore. And this I skip. And this leads now, we have a beautiful determinantal equation for the bar sextic. This was found by Young-Vacho. And I will, the meaning will come later via the theory of cubic determinants. So this is just linear forms, a 3x3 matrix of linear forms bordered by quadratic functions and the cubic functions. So there is this determinantal equation, which corresponds to a representation as the discriminant of a cubic hypersurface. Now, let's see. This was a subject. Take a cubic hypersurface and the linear subspace contained in it. And then if L is contained in the smooth locus, we have some bound for the dimension. 2k is at most n minus 1. Now, I think I skipped this. Here I'd like to mention that I'm using some lovely result by Alberto Collino, who died recently. And if we take L, we can project from the complement of L to a skew projective space. We separate the variables in z's and k's and x. And now, of a point here, x, is just a projective space of dimension k plus 1 with coordinates c0, ck plus 1, and intersecting with the cubic gives L, which is a hyperplane in this space, plus a quadric. And it boils down that if you take the equation of x as you developed in the variable x, this is degree 1, so it's sum of aij, zi, zj, plus these are quadratic in x times zi plus g, then you get a matrix where you get some linear forms, quadratic forms, and g. And the discriminant of this pair, the linear subspace contained in the cubic, are the points in the projected projective space, such that this quadric is singular. So these are the points where this determinant vanishes. So the meaning of determinantal equations where the diagonal degrees are all 1s and then 3 are just that you've taken a discriminant of a cubic hypersurface. And so Togliatti quintics are discriminants of a Togliatti cubic, one with 15 nodes in P5. And the 31 nodes consist of an even set of 16 nodes plus 15 nodes projection of 15 nodes. For sextics, we have some other but more complicated description. The bar sextic is a smooth point of an irreducible component of this variety of dimension 18, and it is a discriminant. Each such sextic with 65 nodes is the discriminant of a cubic hypersurface with 31 nodes for the projection with center a plane passing through 3 nodes. So this is a description of these sextics, similar to the case of quintics, and it allows to show that you get an explicit family. And okay, so well, let me try to finish. Now, there comes one quite interesting question of projective geometry. The maximal number of nodes a cubic hypersurface, a nodal cubic hypersurface can have, is known. is dimension 3, is in P3 is 4, then is 10, 15, 35. And equality for even dimension is attained by the Segre cubic. So this Segre cubic is fantastic. It's given by a very simple equation. The first Newton function, so the sum of the coordinates plus the sum of the cube is called 0, and the sum of the cubes of the coordinates. And these nodes can be easily seen. You just take a half of points plus 1 and the other half of minus 1. And for odd, Goryunov also produced a cubic with the maximal number of nodes. I will skip this. And for lovers of projective geometry, there is a very nice question motivated by a result shown by Kaplan and Frapporti. Any equisingular, so this is some local unicity of the Segre cubic. Any equisingular deformation of the Segre cubic is projectively equivalent to the Segre cubic in even dimension. And the same occurs for the Goryunov cubic in odd dimension, at least in dimension at least 7. Now this is important. Segre, around 1880, had a long memory showing that the nodal maximizing cubic is projectively equivalent to the Segre cubic. A similar result is false in P5 as shown by Togliatti, but these previous results leads to the following natural questions. Is it true that every nodal maximizing cubic, so every cubic with the maximal number of nodes, which is known, is projectively equivalent to the Segre cubic for even dimension of the projective space, or to the Goryunov cubic for M odd at least 7? Yeah, this is tantalizing question, and I hope it is. I think it's important to also pose not only have new theorems, but pose new questions. And thank you very much for your attention.
Okay. I hope you hear the claps for your talk. And it's a beautiful talk in which you conveyed a lot of information and feeling about the amount of things that are connected to the subject, projective geometry, algebraic geometry, algebra, combinatorics. It's and a lot of open problems. And let me ask if there is any question about your talk.
I have a small question. It's very basic. Just to understand the philosophy, if I understood well, this kind of bridge between shortening of codes is the coding theory aspect of partial smoothings, unobstructness, and so you can smooth independently starting from the maximal number of nodes, so you can show the no gaps result. I understood well?
Exactly, that's exactly the point. Thank you for the question. It's a famous result. So I think Manfred suggested to Burns and Wall to use surfaces with many nodes and high degree to show that the deformations, you see, I say the Segre cubic is obstructed. There is this thing, which means, you see, if you have a node, it has some deformation space, and you can try to smooth one point at each subset of points independently. So this is now seems to be possible for small degrees. And this shows, like for instance, for K3 surfaces, Yeah, obstructed. So once you have the Kummer surface, you have, the main theorem says that you take, for instance, this Newton-Cefalu surface, and then you take small variation of the parameters. And then you get locally, you get like a stratification, which is given like independent coordinates for each smoothing. Okay, and so you get not only the possible, all the possible number of nodes, but also the Torelli type picture shows that whenever you have a subcode, you have a shortening, this is in the limit. Okay, and so you can describe the dilemma, which is simply to understand that once you deform a certain number of nodes, and so let me say one thing, that a list of the possible nodal surfaces was done by Ron in 1880. Now, I quote Endras, who was a student of Barth, and he says that this classification by Ron has some gaps. And these codes for extended codes for quartic surfaces were also described by Endras, but he describes these codes through pictures like black and white dots. Some colleagues here, Kirmayer and Kurz, they provided me some computer list, but okay, this was very useful to me to check that mistake. But in a sense, I insisted, of doing the linear algebra to prove that each subcode is a shortening of this Kummer code. And then, of course, I also produce a list, and this list is not is quite readable because I take this vector space of polynomials of degree at most 2, and then I give explicitly all the vector subspaces in terms of functions. And the same thing can be done for other Käfer surfaces. And yeah, everything works well, degree 4, 5, but 6 is really a mess.
More questions? I have a question. Do you know any component, any obstructed component of the Severi variety?
Obstructed?
Obstructed component.
Yeah, as I said, there are components which are obstructed for high degree. You take the Segre hypersurfaces and so on. But not for degree smaller than 6. So, so I think for degree up to 5, they should be unobstructed. And this is based on the study of the geometry of the final varieties of lines on QB hypersurfaces in P4. So I should say that it's also another beautiful research with, there are many people studying cubic hypersurfaces also from the point of view of rationality, but as soon as you get so Pollino studied the linear subspaces of smooth Fano hypersurfaces, but as soon as they become singular, you see it's become singulars. It turns out that if you take the Segre cubic with 35 nodes, all the plates contained in it are contained in a linear subspace of dimension 3 contained in X. So the study of these linear subspaces is extremely, I think it will be extremely interesting also for other questions, period maps of cubic hypersurfaces, which is quite fashionable. It will be very important for rationality questions, but it's it really requires a lot of experimenting, also computer experiments. I mean, these results of Kaplan and Fraporti, a part is done with representation theory, but the unobstructedness, it's really was first done with the computer. So we have to, and are still working on the study of these linear subspaces. So to answer your question, we don't understand we understand in some way the sexy with 65 nodes, but somehow we're reducing them to cubic hypersurfaces with 31 nodes in P6. And these are, we can look at them around the semi-cubic, but in general, we would need some statement about deformations.
Okay, thanks. More questions?
If the chairman allow me just two words, not a question, but I want to say two words because I was the proponent of this colloquium, and there is a relation with what Ciro said before. I am one of the members of the generations of algebraic geometer who are indebted to Fabrizio since I was a Shaki PhD students in front of him, Ciro, Edoardo Cernesi, and Alessandro Verra, and other people who are milestones in Italian algebraic geometry. And so simply Dankeschön für alles, Fabrizio.
Okay. Good. Okay. So if there are no other questions, let's thank the speaker again. Thank you everybody for coming to this session.